Now, last time we learned about potential energy. It's only associated with conservative forces, and the two most important kinds are gravitational and elastic. Now, today we're actually going to learn how to use this energy to solve for useful things. And that's usually going to happen by conservation of mechanical energy. And this term mechanical energy just means the sum of the kinetic and potential energies. And when we say it's conserved, that means it stays constant, the amount of it doesn't change. And in general, it will be conserved if no non-conservative forces do work. In practice, that means if you can neglect friction and air resistance. And when that's true, the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. Here's an example. If you have a block hanging from a spring, you pull it down, you let it go, it starts oscillating. There are three kinds of energy involved here. There's gravitational potential energy, there's kinetic energy, and there's spring potential energy. When it's way down at the bottom of its path, the spring potential energy is large, the gravitational potential energy is small, and the kinetic energy is 0. But then at the top of its path, US is small, UG is large, and once again K equals 0, but the sum is the same in both cases. Now let's look at an example of how we would use this. So we've got a 4.5 kilogram rock, and we're going to drop it onto a vertical spring with a given spring constant, and we want to find the maximum compression of the spring. So if we draw the system at the beginning, here's the ground, here's the spring, and we'll interpret the height, h, as the height above the spring. So the spring right now is unstretched. So this is x equals 0. And for convenience, I'm going to make that our 0.4 gravitational potential energy as well. And then it's dropped. And when it lands on the spring, and it compresses the spring a certain distance, and that distance we'll call x. And we're going to use energy to find out what x is. There are three kinds of energy here. There is the kinetic, there is spring potential, and there is gravitational potential energy. Now, initially, Ki is 0. Also, the spring potential energy is 0 as well, because it's not stretched or compressed. But the gravitational potential energy is going to be mgh, because we're taking the unstretched length of the spring to be the 0 point. The final kinetic energy is also 0. That's an important result, and it's not as obvious as the fact that the initial kinetic energy is 0. Because at the maximum compression of the spring, the block is changing from moving downward to moving upward, and so that means its velocity is instantaneously 0 at that point. Now obviously the spring potential energy at the end is at a maximum, and it's equal to 1/2 kx squared, where k is the spring constant. And the gravitational potential energy is actually going to be negative because we're below our 0 point. So it'll be negative mgx. And now, because there's no friction or air resistance, or at least we're assuming there's none, we can set the initial energy equal to the final energy. So mgh is the initial energy, equals the final energy, 1/2 kx squared, minus mgx. Now notice that x's are unknown, so we've got a quadratic equation here. And when we have a quadratic, we get everything on one side of the equation. And the easiest thing to do at this point is plug in numbers. When you do that, you end up with 1/2 k is 47.5 x squared minus mg is 44.1 times x, minus mgh is 61.7, and all that equals 0. Now you use the quadratic formula or solve it however you want, but you'll get two answers. X equals 1.69 meters, or x equals negative 0.77 meters. We'll throw out the negative one and say that the block compresses the spring by 1.69 meters, which is pretty substantial. But notice 95 newtons per meter is not a very stiff spring, and 4.5 kilograms is about 10 pounds, so it's a pretty big rock. Now we move on. Now there's a whole class of problems that have to do with loops and roller coasters. So let's say we have a very simple roller coaster. It starts from a hill of height h, goes down to the ground, and then goes around a loop of radius r. The question is, what does the initial height of the roller coaster have to be in order for the coaster not to fall off when it's right here? Now you might think that it would be sufficient for the cart to start there because, after all it needs to do is get up past that point. But that's not true, because there's a certain minimum velocity that the roller coaster has to have at the top of the loop in order to avoid falling off. To find that minimum velocity, we have to use dynamics. So remember, for a free body diagram of the roller coaster at that point, there's going to be gravitational force pulling down on it. There's also going to be a normal force from the track. So we can say that ma equals mg plus n, that's just Newton's second law. But it's going in a circle. So the acceleration is v squared over r. And notice that the larger v is, the larger n is going to be. The minimum velocity is going to come when n equals 0, because that represents the point at which the roller coaster falls off the track, loses contact with it, no more normal force. So we'll say n equals 0, divide both sides by m, and find that the minimum speed is given by the equation v squared equals g times r. And I could say v equals the square root of gr, but I'm going to leave it like that for reasons that you should see shortly. Now once we know that that's what the minimum speed has to be, now we can use conservation of energy to find out what the height has to be. So initially, the kinetic energy is 0, the potential energy is mgh. At the top of the loop, the kinetic energy is 1/2 mv squared, but v squared is gr, so it's 1/2 gr. The potential energy, measured from the ground, it's at a height of 2r. So this time the height is 2r, so we get mg times 2r, 2mgr. Oh, left off an m here too. And now we use conservation of energy. We set the initial energy equal to the final energy. We get mgh equals 2mgr plus 1/2 mgr. Notice that we can divide the entire equation by mg, and a little bit of arithmetic gives us the height equals 5/2 times r. And that is our solution. One of the wonderful things about gravitationally driven systems is that m and g frequently cancel out of these things. It's a simple idea. It has many, many applications. The way you're going to get good at those applications is by working problems. So what you need to do are questions 3 and 5 for tomorrow. And next time we'll talk about graphs of energy versus position. See you then.